Right. Hello everyone. Today we are coming to look at mass transfer processes. Yes, so mass transfer processes. So the first thing we'll be looking at is diffusion. Right. So we'll be looking at diffusion. Right. How to evaluate concentrations. How to evaluate mass concentration, molar concentration. How to evaluate velocities. That's where we have the mass velocities. We have the molar velocities. Right. How to evaluate them and how to evaluate flux, right? So we have the diffusive fluxes, right, and how to evaluate the diffusive fluxes and the flux, right? So let's see how to evaluate all these things using and even the Fick's law and those things. So let's see how to evaluate them by using an example, right? So from here, let's look at our first example. So our first example over here, as you can see over here, we have they say that we have a mixture of noble gases. So we have helium, argon, krypton, and xenon, right? It's at a total pressure. So the total pressure we are talking about over here is 150 times 10 raised to the power 3 Pascal, right? Then they had a temperature of 500 Kelvin. Right? It said that if the mixture has equal mole fractions of each of the gases, right, and we know that mole fractions always add up to 1, and we have 4 gases over here, meaning that the mole fractions of each of the noble gases will be 0.25, right? So that you can get 1, right? And they are telling us to find the composition of the mixture in terms of what mass fraction, right? So in terms of mass fractions, right? So let's see how to find it in terms of mass fractions. So first of all, what we do is that I'll assume that I'm using I'll assume a basis, right? So I'll assume a basis of 1 mole. If I assume a basis of 1 mole, meaning that helium is having 0.25 mole, then argon is also having 0.25 mole, then the krypton is also having 0.25 mole, then xenon is also having 0.25 mole, right? So having all these things, we know this formula from chemistry that the number of mole is equal to the mass divided by the molar mass, right? So you can actually calculate for the masses using this formula, right? But first of all, you have to get the molar masses of each of them, right? So the molar mass for the molar masses, and so for helium is 4, right? Then for argon is 40, then for krypton is 84, then for xenon it becomes 131. That's the molar masses, right? So computing the masses of each of them, right? So the masses, right? So it will be for helium, right? The mass will be 4 multiplied by 0.25, right? Which gives me 1 gram, right? So that means the molar mass is in gram per mole, right? Molar mass in gram per mole, so that we have this one in grams, right? Then for argon, which is 40 times also 0.25, that one too gives me 10 grams, right? Then I'll go to krypton, which is 84 by 0.25. I'll get 32.75 gram. Then I move to, sorry, over here, I'll get 21 grams. Then for the xenon, which is 131 times 0.25, I'll get 32.75 grams. So over here, getting the masses, I can actually get what the mass fractions, right? Since they want the compositions in terms of mass fractions, right? So if I want the mass fractions, it becomes what the mass of each component, right, divided by what the total mass, right? So if I add everything over there, right? If I add everything over, the total mass gives me 64.75 grams, right? So taking that one into account, for I'm still on the A. So taking that one into account, helium, right? The mass fraction of helium would be 1 divided by 64.75 grams, right? So that gives me a fraction of 0.015. Right. Then we do similar thing for argon. So similar thing for argon will lead us to 0.154. Then we also do for krypton, which leads us 0.324. Then for xenon, that one becomes 0.506, right? So right now I've calculated the compositions of the mixture in terms of what mass fractions, right? So that's for the A. Right, and the B was telling us to also calculate for the average molecular weight of the mixture. Right, so for us to get the average molecular weight of the mixture, since I already have the mass fractions, right? So it's either we have two approach, right? So it's either you use the average molecular weight will be equal to the mole fractions, right? So it's either um y1 m1 plus y2 m2 plus y3 m3 plus rho. Then is so that's when you are using the mole fractions, or when you are using the mass fractions, y1 over m1 plus y2 over m2 plus y3 over m3, right? So it's either, sorry, yeah, I mean, let me use x for the mass fractions, right? So it's either use the mass fractions or use the mole fractions, any of them work. So I'm coming to use the mass fractions to work. So I have 1 over the average molecular weight giving me, so the first one, I had 0.015 divided by 4 plus 0.154 divided by 40, then plus 0.324 over 84, then plus 0.506 divided by 131. Right, so computing the right hand side, right, I'll get 0.015391. So if I want the average molecular weight, right, that's the inverse of that one over there. It gives me 65.27 gram per mole. Right. So this is the B. Right. So I've actually calculated for the average molecular weight, right, which is 65.27. Right, 65.27 gram per mole. So let's go to the C part. Yeah, so let's go to the C part where they are asking us to calculate for the total molar concentration, right? So the molar concentration we're given by P over RT, right? And we know from we had pressure 150 Pascal, right? So 150 times 10 to the power 3, and the R 8.314. Then I have my temperature was 500, right? So if the temperature my temperature becomes 500, right? So this leaves me with a concentration of 36.08 mole per meter cube, right? So that's the total molar concentration, right? So that's for C. Then let me see D, which is the mass density, right? So the mass density, you can either use PM over RT, which is a long approach, but you can also use the mass density, which is equal to the molar concentration times what the um average molecular mass, right? So this one I got 36.08. Then I multiply this one by the average, which was 65.27. Right. So getting this one will lead me to the mass density. So 36.08 multiply 65.27. Right. So I'll be getting so per doing this one, I'll be getting 2354.94, right? But this one give me in gram per meter cube, right? But it's mostly in kilogram per meter cube, so to be 2.35 kilogram per meter cube, right? So that's actually the mass density, right? So for us to actually get this, when you are doing mass transfer, you need to be able to know the masses of I mean the concentration of species, whether it's the mass concentration or the molar concentration, and even the fractions, the average molecular weight of everything, right, in the mixture of gases that we have, right? So this is the number one, which is quite a very simple example to actually do, right? So let's see the second question, which talks about a flue gas, right, consisting of carbon dioxide, oxygen, water vapor, and nitrogen, right? And they give us the mass, they give us the molar fraction, right, of CO2 and O2, right, respectively. And then the weight fraction of water was given as 6 points. So you can see that although we have the gas, but there are different constituents. You can see the CO2 and O2, they give us molar fractions, but for weight fraction, for the water, they give us weight fraction. Virtually, we actually have to convert from one point to another before we can actually can actually solve the question, right? So what you'll be doing is that first you first have to know the molar masses of each of the compounds, right? So CO2 has a molar mass of 44, then O2 has a molar mass of 32, then H2 has a molar mass of 18, then nitrogen has a mass of 28, right? So since we have all the molar masses over here, right, I'll assume a basis, right? So I'll say I'm assuming a basis of 100 mole, right? So I'm assuming a basis of yes, let me assume a basis of 100 mole. Yeah, that's fine. So a basis of 100 mole. So if I assume a basis of 100 mole, meaning that CO2, right, will be having a number of moles of 12 mole, right? Then oxygen will be having at 6 mole. Right, so I have that one over here. Then I can see that I can let H2, right, to be equal to X. Right, so I say, so this is the so most of what H2 should be equal to X. I don't know that one. So if the most of H2 is equal to X, that means that the most for the nitrogen, right, becomes 100, right? Since the total mole is 100, right, it becomes 100 minus 12 minus 6 minus what, this X, right, which gives us 82 minus what, X. You get it? And over here we can also calculate for the total mass, right? So you can see that the total mass, right, becomes, so if you want to calculate the total mass, you know how to calculate for mass, which is the number of moles times the various molar masses, right? So for CO2 is 12 times 44, right? Then for oxygen is 6 multiplied by 32, right? Then for water is 18 times x, so 18x. Then for the nitrogen, it becomes the 82x, 82 minus x, right? This one multiplied by what, 28. You get it? Over here, you can actually compute what the total mass, right? So computing, we are be getting 720 plus 18x. Then I'll be getting plus 2296 minus 28x, right? So doing the math, I'll be getting 3016 minus 10x. Right? So this gives me the total mass, right? If this one gives me the total mass, I can use the mass fraction of what, the water, to actually find my x, right? So I see that mass fraction, right, of what, H2 will be equal to what, the mass of what, H2 divided by what, the total mass. right? And I know the mass of H2O, right? So the mass of H2O is 18 times X, right? Yeah, so that's the mass of H2. That's the molar mass multiplied by the number of moles divided by the total mass, which is this minus 10x. Right? So having this one and the mass fraction of water was given, which is 6.17, right? Which becomes 0.0617 will be equal to 18x over 3016 minus 10x. Right? So solving this equation for x, x would be 9.99, which approximately 10 moles, right? So that means that the number of moles of the water is actually 10 moles, right? 10 moles, which is 10%, right? So yeah, I have just 10% over there, right? So the question asks us to estimate the density of this gas at 500 and that's on. So you need to estimate the density, but since we don't have all the components in just one form, I mean that we don't have them in terms of just mass fraction or just in terms of molar fraction, we can't find the density. So you have to put them in terms of the same compositions before we can even solve the question, right? So right now we can continue to actually calculate for the um the concentration, right? So they told us to find the estimated density, right? So estimating the density, you have rho which will be equal to PM over RT, right? So PM over RT, and I know we have the pressure to be 110 kilopascal times 10 to the power 3, right? So for me to even do this one, I need the average molecular weight, right? And this is 8.314. Then pressure was 500, right? Pressure was 500. So for me to even do this one, to have to calculate for the average molecular weight, right? So I can use the mole fractions to do. So the average molecular weight becomes the mole fractions, right? So I have for carbon dioxide, right? For carbon dioxide, it was given as 12%, right? So 0.12, and oxygen was 6%, right? So I'll have 0.12 times 44 plus 0.06 times 32, then plus for water becomes 0.1 because I got 10% times 18, then plus. So for nitrogen, you can see that over here the nitrogen was 82 minus x, which is 10. So nitrogen becomes what? 72 moles, right? So nitrogen becomes 72, 72, right? Nitrogen becomes 72. So we need to actually calculate for um, the since we have this one, so we can continue. So we have 0.72, right? So 0.72 also multiplied by 28. That's for the nitrogen. Then so this one leads us to an average molecular weight of 29.16 gram per mole. Right. So having this one, I'll put it over here. So I'll get 29.16. But since in terms of we want the density in kilogram per meter cube, right? So I convert the grams to kilograms. So that means I have to multiply this side by 10 to the power minus 3. So if it comes down over here, it becomes to the power 3. Then I'll get 0.772 kilogram per meter cube, right? So that's the density, right? So the tricky part was to actually calculate for the number of moles for the water since they give us mass fraction, right? So we had to calculate for that one. Then we calculate for the nitrogen too, so that you can use that to find the average molecular weight, so that can help us to find the density, right? So that was the tricky part about the second question, right? Yeah. So let's look at the third question where we have to evaluate, right? Where we have to evaluate some things. Yeah, so the third question, they are telling us to evaluate mass velocity, molar velocity, right? So over here, we are talking about the when we are so We're talking about the mass velocity, right? So the mass velocity, which is V, right, will be equal to the summation, right, of the mass concentrations multiplied by their individual velocities divided by the total velocity, right? And the molar concentration, which is also given as summation of molar concentration times the individual velocities, so divided by the summation of the velocity, right? So this is what you're coming to actually use to calculate for the molar average velocity and molar average that one, right? So and we've been also asked to also calculate for the flux, right? So the J, there are diffusive flux, right? So we have diffusive flux, right? And the N there is the flux, right? So you have the mass flux and you have to calculate. So the small n is the mass flux, the big one is the molar flux. The small g there is the mass diffusive flux, then the big J is the molar diffusive flux, right? So you can see that this one, the small one, right, will be given by the Ci, right, minus the change, right? So it becomes the individual minus the average, the molar average velocity, right? And for the sorry, this is the mass, so it becomes this one without any star, so just this one, right? Then the big one becomes the Ci Vi minus the V star. Then small n, right, is just multiplying these two, right? It's just this one, and the big one becomes this one. Yeah. So right now we have all the formulas that we'll be dealing with to solve our question, right? So this is what you're coming to solve our question. So for us to solve this question, we need to calculate the densities of each of the components and the concentration of each of the components too, right? That's what you're coming to do. So for us to do that one, so let's start with A, which is asking us to calculate for the mass average velocity and that one too. So we know that the density or the mass velocity, um, the density or the mass density becomes Pm divided by RT, right? So let me calculate for the total density. So they give me um, a pressure of 150 kilopascal to the power 3. Then um, I don't have molecular weight, so that means how to find it. Then this one is 8.314. Then they give me a temperature of 295, right? So the average molecular weight, right, using so they gave me the fractions by volume, which is the same thing as by mole, right? So the nitrogen is 0.2, and the molar mass for nitrogen becomes 2, then plus that, so I have oxygen 0.4 times 32, then water is 0.4 times what, 18. So that gives me the average molecular weight, which gives me 20 point which gives me 20.4. So which gives me 20.4 gram per mole. Right. So this becomes 20.4. As I said, we want it in kilogram per meter cube. So you convert the grams to kilograms, right? So we have 1.248 kilogram per meter cube, right? So you have this one as a total. That's the total mass concentration, right? So total mass concentration. That means you have to find the individual ones, right? So the mass concentration of hydrogen would be its fraction, which is 0.2. So you are finding the partial. So it becomes the partial pressure. Since the pressure, total pressure is 150 times 10 to the power 3, the partial pressure is the fraction times what the total pressure, right? Then I also multiply by its molar mass, which is 2. Then I divide by 8.314 times 295, also times 10 to the power 3 because of the molar mass. So this one I get 0.0245 kilogram per meter cube, right? Then I also do the same thing for oxygen, which is 0.4 times 150 times 10 to the power 3, also times 32 divided by 8.314 times the 295 times 10 to the power 3. So this one gives me 0.7828 kilogram per meter cube. Right. Then I also get for H2O, right? So that one is 0.4 times 150 times 10 to the power 3 times 18 divided by 8.314 times 295 times 10 to the power 3. So this one gives me 0.4403 kilogram per watt meter cube. So right now I have the individual, right? So if I have the individual ones, that means I can get the mass average velocity, which is the summation of VI divided by the total density, right? It's the total density, not the total velocity. Sorry for so that's the correction, please. The mass velocity is the rho I VI over the total rho, not the total V. Yeah, sorry for that. So this one becomes 0.0245 times its velocity, right? Its velocity was given in the question. So velocity for hydrogen was given as -10, then plus 0.7828. The velocity of this one was -2, then 0.4403, also times 12, right? All divided by the total, which is 1.248. So that's the total mass concentration. So this one gives me um, 2.78 meter per second, right? So this one gives me the mass average velocity V. So right now I have to calculate also for the molar average velocity, which is the V star, right? So for me to also get that one too, we also follow the same approach, right? Right, the same approach, just that I have to use this one, right? You know that we know that C is equal to rho over M, right? So here, so I can actually use this one where I have 1.248 divided by the 20.4, right? So this one is in kilogram per meter cube. This one can be in gram per mole, right? So I have to make sure I multiply this one by 10 to the power -3, such way that I'll get it in terms of also kilogram, so that I can work with it, right? So it's 1.248 divided by 20.4 multiplied by 10 raised to the power -3. Right. So this one gives me a molar concentration of 61.18 mole per meter cube, right? So this is the total concentration too. So if I have the total concentration too, that means I can also calculate for the individual concentrations. So the individual concentrations for the hydrogen, right? It becomes its mass concentration 0.0205 divided by its molar mass, which is 2, but times this one to actually get it in terms of. Then this one also becomes 0.7828 divided by 32 1 minus 3. Then this one also becomes 0.4403 over 18 multiplied by 10 to the power -3, right? So that evaluates that one, right? So we have 0.0245 divided by 2 times 10 to the power -3, right? So this gives me a molar concentration of 12.25 mole per meter cube. Then for the next one, right, which is the oxygen, right, I have 32. So this one I have 0.7828, right? So that one too gives me 24.46 mole per watt meter cube. Then I'll have this one too, which is for the water, right? So the water I'll have 24 So I have 24.46 mole per earth meter cube. So that one to also go through a similar thing to also calculate for that one. So that one I'll be having the V star will be equal to summation of CIVI over the total at C, right? So I'll be having 12.25 times minus 10, right? Plus 24.46 times minus 2, then plus 24.46 times 12, all divided by 61.18. Right, so that will give me that value, right? So I'll have 12.25 multiplied by minus 10 plus 24.46 multiplied by minus 2, then plus the next term becomes 24.46 also multiplied by 12, then divided by 61.18. So I'll be having 1.996 meter per second, right? So this one gives me the average molar concentration. So you have to make sure you work it out. And please, when you are working it out, make sure your unit conversions are valid. The molecular weight, which is in gram per mole, make sure it's in kilogram per mole before you put it inside your question. Right, so that the units will be at consistent. If you go and put the gram per mole there, that means your answer will be to be some way. Although you get your answer in terms of gram per meter cube, but you make sure you put it back in kilogram per meter cube so that it will be consistent with the other things that you are solving for. So this is what we are actually getting for this one. We are getting 1.996 meter per second, right? So now we can calculate for the other things. So that's for the A, right? So the B says that we should evaluate the four fluxes. So you're evaluating all these things just for the oxygen. So J, right? So this is the mass diffusive flux, right? So the mass diffusive flux of oxygen, right, becomes the density of oxygen, right? The density of the oxygen, density of oxygen coming. So it becomes the um. So we want for the oxygen. So that one becomes so it becomes the density of oxygen, then the um, of oxygen minus what's the V. So here the density of oxygen was 0.7828, then multiply by the velocity for the oxygen is what that's the second thing, so it's minus 2, then minus this one was 2.78. So we have this one to actually calculate for that one. So this one leads us to minus 3.74 kilogram per meter squared second, right? So that's it for this one. Then we have the flux, right? The mass flux, right? So this mass flux is the density of oxygen multiplied by the velocity of oxygen. So this one 0.7828 multiplied by minus 2. Right. So we have 0.7828 multiplied by minus 2, which gives us minus 1.56. Right, let me say 566, right? Minus 5.566. Right, and yeah, minus 0.566 kilogram per meter squared second, right? Then the big one becomes the concentration of oxygen times the velocity of oxygen minus the molar average velocity. So this one is 24.46 multiplied by minus 2, then minus 1.996. Right, so now we're getting 24.46 multiplied by minus 2 minus 1.996. 1.996, right? So I'll be getting negative 97.742, right? So I have mole per meter squared second, right? Then for um, NO2, which is the molar flux, right? So the molar flux becomes the of oxygen multiplied by the velocity of oxygen. So 24.46 times minus 2, right? Now 24.46 multiplied by minus 2, right, which gives me minus 48.92 mole per meter squared second, right? So you actually have to just remember the formulas, know the difference between diffusive flux and the difference between just the flux, right? So the N is the flux, so the small ones are the mass flux, right, and the big ones are the molar flux, right? You have the molar diffusive flux, the mass diffusive flux, right? So that's it for question number 3, right? That's it for question number 3.